Okay, so last time we were looking at basically for the first time how to price American style options using the binomial option pricing model of Cox, Ross, and Rubenstein. Now, we've gone through all the details for how the trees are constructed, and we know already how to determine the price of a European option. What is different here is that with the American style option, we have to allow for the possibility of early exercise. So let's just go back and revisit what we were doing. Let's say we have a two-period model here. We have a stock price S today, T equals 0 is today's time, of course. And then in time one, the stock price can either go up to SU or down to SD. And of course, U is a constant, D is a constant. And they are designed on purpose to make sure that because they're inverses of each other, going up and then down brings us back to the same location as going down and then up. Okay, so what that means here is it may not be that obvious from this diagram, but these two values are going to be the same because U and D are inverses of each other. So this has a lot of advantages, this approach. It means that the tree has a very nice regular structure, and it makes it easier to calculate prices on this tree using different formulas, and it has a lot of nice convenient properties. Later on, researchers developed trees where this wasn't necessarily the case, and they may have believed that there was some more realism being introduced into the trees, but at the cost of a great deal of extra complexity. But the Cox, Ross, and Rubenstein model, the very first one, was really designed more than anything else to help us understand what the Black-Scholes model is actually doing. And they really never expected that this would prove to be so important because it was really more of an academic exercise. Hey, everyone, what is the Black-Scholes model actually doing? But of course, once it became clear that this could be used for American options, that was a huge deal because, of course, at least now, most options are American style. And so the Black-Scholes model was wonderful, but it was also very restrictive. And of course, later on, other papers were released showing other ways in which the Black-Scholes framework could be extended to price other types of options. But this Cox, Ross, and Rubenstein framework proved to be a very big step forward. Okay. Anyway, so recall that once we have the stock price tree in place, and also, once again, let's remind ourselves that U is equal to, not R, sigma times the square root of delta T, and then D is the inverse of that. So the idea here is that they wanted to make sure that they're inverses of each other, but also if you were to do the calculations, you would see that this does replicate the binomial distribution. That's really what they're aiming for. The model has to replicate the binomial distribution, and otherwise it's not going to match up with the Black-Scholes model. And of course, the reason for doing this is because in the limit, as this steps between these time steps shrink, the binomial distribution will converge in the limit to the normal distribution. And of course, in the Black-Scholes model, rates of return are assumed to be normal. So that's really the logic behind a lot of this, trying to replicate Black-Scholes assumptions that we have this nice structure that the stock is following, which in the limit implies that the returns to the stock are normal and that the price of the stock itself is log normally distributed. And we'll see more about this as we go along in the course. But so this is how the stock price tree is set up. And then the options, now this is where it gets a little messy if these are American style options. With European, what we notice is that in two time steps, when the option matures, the payoff is the value of the option. So for example, FUU, if you notice, is simply the payoff to a call option at that node. And of course, if you look back at the tree, you'll see that if the stock price goes up twice, it reaches SU squared. So here, you notice how that is the value of the stock. We compare that with the strike price to see if the payoff is positive or not. Okay, so in other words, these nodes at the end, which are called the terminal nodes, are where we find that the options value is exactly equal to its payoff if exercised at that point. The interior nodes, though, are a little bit different because what you're doing here is you're taking the expected value of the option, given that we have two possible values in one time step. And actually, I'll tell you what, let me draw another little graph here so we can see it more closely. Let's use FU as our example. In one time step, either we're going to go up to FUU or down to FUD. So the expected value of this in one time step would be a weighted average of the two possible values, FUU and FUD, weighted by the probabilities. So that's the expected value. And but the option price itself is not equal to that amount because those cash flows take place in the future. So today, from today's perspective, the value of this option FU has to be the present value of this expectation. Now, of course, we'll remind ourselves that we're using continuously compounded rates of interest. So you can see this e to the minus r delta t. And that tells me two things, that the annual rate of interest is r, which is the risk-free rate of interest. Delta t is the time step. Okay, so in other words, if these two cash flows occur in 6 months, delta t would be 0.5 to indicate that this is only half a year in the future. So all the interior nodes are priced in the same way. We're calculating what is known as the present value of the expected future cash flows to the option. So, and in fact, that would be the case for any asset that we chose to price on a trade like this. This is not unique to options. What is unique is the payoffs at maturity. And for the American style options, the fact that we can exercise them early, which means we have to make a decision of some kind. So, yeah, let me just quickly put these in here as well. Just a quick reminder that here, because this is the last period of the option's lifetime, these we can fill in as well. Now, this is all fine for a European option. In this case, a European call. And of course, if this was a put, it would just affect the payoffs at the end. Otherwise, the rest of the tree would be the same. Now, for the American version, we have to make one very important change, which would be what? All right, let's find out. So we just started to talk about this last time. And again, we'll stick with a single node because, of course, I can apply this to all the other interior nodes. So what's changing here is FU itself. So one of two things is going to happen. At node FU, the option will be exercised or not, depending on Now, what does it depend on? Okay, well, let's think about this. If the option is exercised early, let's just make a note of this down here. If exercised early, we receive the payoff to the option. And that would be max SU minus K0. Okay, so it would be as if the option matured at that point in time. So the payoff is actually max SU minus K0 because that would be the value of the stock on the tree. But if not, then it has the value we saw in the previous slide. If not, the option is worth E to the minus R delta T, P times FU plus 1 minus P FD. So what we do is we decide based on which of these two is the greater amount. So the option will be exercised depending on whether or not the early payoff exceeds the expected present value of E to the minus R delta T, PFU. Sorry, this should have been UU and UD. Sorry about that. So you're just basically comparing the two and seeing which one is the greater. So think of this as the amount that the option is worth if it's not exercised early, because that's the amount it would be worth as a European option. But as an American option, there's a possibility at least that instead this payoff amount would be even greater. And if so, then you would exercise early. Okay, so you could write this on the next slide in the following way. If, and again, this is just for the FU case. The others will be a little different. So if the max of SU minus K0 exceeds this amount, then the option will be exercised early. Otherwise, it won't, because it would make no sense. Okay, because remember, when you exercise early, you're giving up the time value of the option. You lose all of that. You're basically trading the payoff for the remaining time value. So you got to make sure that you're doing the right thing. And this is how you would do that. So we're assuming in the model that everybody will always exercise early when it makes sense. Nobody will just forget to exercise or some nonsense like that. So we'll assume that if it's possible, people will exercise it early. So here, this is how we make that decision. Otherwise, the option will not be exercised. It's as simple as that. This decision is made at the interior nodes. Once we reach the maturity date, it's too late. It's now equal to the payoff. End of story. Okay. So with that being said, yeah, I think okay, so this is pretty much exactly what we've been doing. And you know, the other thing I wanted to remind us is that if this was a put, this is the only thing that would be different. These payoffs at the maturity date would reflect the fact that this is a put. Who remember the call has a payoff of max S minus X and zero, or here we're using K's, and the put is max K minus S zero. So, and you can see here, this part depends on what node we're on. So that would be literally the only change you would make if your option was European, if your option is a put rather than a call. Okay. And then of course, for European only puts, we do not have the early exercise feature. And of course, it's only for American style options where every interior node potentially could lead to early exercise. All right. Now, here we've got some theoretical results about upper and lower bounds for the potential value of a call or a put, depending on whether it's American style or European style. I think that, well, these are kind of important. They're very theoretical. I think it's more important to move on to more, computational issues, shall we say. We'd like to specifically start looking at how all this is done in VBA. And you'll discover that it's surprisingly straightforward to do this in VBA because it has what are called loops, meaning that we can continue to process until something is done. Now, here's a brief review of how Koch-Schwarz and Rubinstein came up with their expressions for U and D. And so basically, these are the ones that are consistent with risk neutrality, as well as the assumptions of the Black-Scholes model, meaning that you can replicate this whole thing with the binomial distribution. And so here's some specific numerical examples. Let's see if we can find one. Yeah, these are American. Let's try and see if there's an American example here that would work for. I'd like to show you an example where we have at least one early exercise. Now, sometimes with these trees, if we don't have a whole lot of steps, the option never gets exercised early. And you end up with the same price as between an American and a European option. What you end up doing, once you've written your code, by the way, what you're going to end up doing is you're going to have as many time steps as possible because that will make your result more accurate. Here we're just illustrating how this process works, but you would never actually try to price an option with 2 time steps. It's just not going to work well. Okay. All right, let's take a look at this one. No, I don't think he got exercise early. And that's all right. We have other examples we can look at later on. Now, here's something else that we'll get back to later on. We haven't actually really spent a whole lot of time with the Greeks. We did a little in the previous course, but it's been a while. So maybe we'll save this discussion for a bit. But the Koch-Schwarz and Rubinstein model has its own approach to calculating Greeks. With Black-Scholes, they're basically taking derivatives of, and I mean calculus derivatives of the Black-Scholes model. Whereas here, there's a way that you can derive these Greeks directly from nodes on this tree. And we will do this, just not yet. I think it would be better for us to go open up our first example in VBA and at least see how this thing is set up. All right, let me go find it. I should have opened this up earlier, but I forgot. All right, hold on. All right, so let's see, which one of these shall we pick? By the way, if you notice, there's a lot of examples in here. Some of these are meant for the Greeks. Some of these are actually, there's one or two examples in here of how to price an exotic option with these trees, which I think we should take a look at. But right now, let's just look at let's start with this simple one. Let's look at the European call option model. Now, okay, so here's what's happened here. This is actually the result of running the model. And you can see all the values that are listed here. This is a European call with a stock price of 100. The strike is 100. It has 1 year to maturity. The risk-free rate is 6%. Now, Q, by the way, if you remember from the previous class, is the yield of the underlying asset. That was set to 0 here because remember, the original Black-Scholes model doesn't allow for that. So we'll, for now, we'll stick with that assumption, but then we'll relax that assumption later on. We have 3 time steps, and then the volatility, the sigma, is 16.5% per year. So down here, the program calculates the constants that we need for the problem, delta t, in other words, the size of the time steps, the probability of the risk neutral probability of moving up. Disk is something that I created. This is the shorthand for either R minus R delta t, and then of course here's U and D. Now, what we could do is draw a graph, but what I'd like you to see is the VBA code. Just take a quick look at it and see how this thing has been put together. All right, now, one thing we do have to keep an eye on is this. The notation for the Black-Scholes model and for the binomial option pricing model are well understood, but they don't really lend themselves well to writing computer programs. What we're going to do instead of the notation that we've been using is we're going to need to replace it with matrix notation, okay? Because the computer is not going to handle this type of thing, SUU and that type of thing very well. So you're going to see that we're going to have to create a lot of matrices in order to implement this program. All right. Now, Excel has that capability. Excel has a feature called an array, which is essentially a general, it could mean, the thing about the Excel array is that it can refer to objects like vectors. It can refer to matrices, but it also can refer to 3-dimensional objects. And in fact, I don't know if there's even a limit to how many dimensions these arrays can have. So the name is a little deceiving. Normally, when you hear the word array, it implies a one-dimensional object, like in other words, a row of vectors, a row vector or something like that. But Excel uses the name array in a very general way. It's an object that can have multiple dimensions. In other words, it's not just rows and columns. It can have, I guess you can think of it as depth. In other words, it can have 3 dimensions in Excel, but we're not going to do that. So what's kind of interesting about arrays in Excel is that the indexing isn't restricted to positive integers like you might think. It can have 0 elements and it can have negative integer elements, which gives it a lot of flexibility, as we'll see as we go along. So I'll tell you what, I just want to quickly show you some of Excel's capabilities in the area of matrix algebra. Okay, so first of all right, so before we do any more, we really need to review Excel's capabilities in this area. So let's just say that we have 2 matrices, and they're both 2 by 2. All right, now, of course, we know how to do this. This is a 2 by 2 matrix. This is 2 by 2, so they certainly are conformable to each other. The result will also be 2 by 2. So here's what you have to know. In order to, let's say, add these together, I don't think it has a separate addition function. I think what ends up happening is you just add it directly. Let me just see if I'm remembering this correctly. I'm going to put equals. Okay, I'm not sure this is going to work. Hold on. Oh my God. Okay, it did work. Let me just confirm that. 1, 3, 3, 3. But there's a trick that you were not able to see. Um, in order to execute a matrix operation in Excel, and by extension VBA, by the way, um, you must use Shift Control Enter instead of Enter. Okay, with most Excel commands, you just type, like for example, equals square root of 9, enter, and you're done. With this one, what I actually had to do, it looks like all I did was type equals A1 to B2 plus D1 to E2 and then hit enter. I did not. I hit Shift Control Enter. If I had hit enter, watch what would have happened instead. Oh, okay, my mistake. And I'll tell you what, they may have changed this in the past. It would have only filled in this one cell. I'm kind of startled to see that, I have to admit. Um, I think it's maybe because I'm not really and truly using one of the matrix operations. It's just plus. I'm not so sure, but you know what? The reality is we're not going to need this feature anyway. All we're going to do with matrices is multiply them. But we also have to learn how to access them as well. Although I shouldn't say that. Sometimes we're going to multiply them by a scalar. So, all right, what else can this thing do? All right, let's try this. So I'm sure subtracting, let's do this, equals this one minus this one to see how it reacts. I'm gonna hit enter, and what do you know? Oh my God. All right, so now again, that's because plus and minus are not actual matrix operations. You'll see what I mean in a minute. There are several predefined matrix operations that must have the shift control enter. So let's see, how is it going to react if I multiply a matrix by a scalar? I want to know what it's going to do if I try to multiply this by 2. Okay, and again, it worked with enter. Good, and I just multiply by 2. All right, now here's where it gets interesting though. Now we're going to multiply. And this time, I'm pretty sure it's going to stop me if I try to just hit enter. So let's try, I don't know, how about 1, 0, 2, 1. Okay, so this time I really do want to multiply them together. So the correct command here is something called mmult for matrix multiplication. So it needs to know where are the two matrices I'm using. Now, I'm going to do it the right way, Shift Control Enter. Okay, then now here I'm going to do it the wrong way. I think what's going to happen is going to only show me the upper left-hand corner, the first cell. No. Okay. Well, you know what? They must have upgraded this fairly recently because it used to be that would never have worked in a million years without the shift control enter. Huh. Wonder what else they changed. All right, well, that's that. So we know we have an example here of adding, subtracting, multiplying by a scalar, multiplying them together. Now, here's one that may or may not be necessary. Inverse. So what I'm going to do is figure out what the inverse is of this matrix. Yeah, I guess they got rid of that requirement because I was able to do it with just the enter sign. Now, I want to confirm that this was done correctly. So I'm going to do mmult. Of course, we know this should give us the identity matrix. There we go. So invert, remember, it's M inverse. Okay. Now, it does follow the standard matrix notation, rows, columns. But like I said, you can set it up to have any indices you want. So I could, for example, at least in VBA, I'm not sure how it would react in Excel if I had like a negative index. But anyway, so let's go into the VBA and look at this code, and we're going to try to make some sense out of it. All right, so again, we know what the graph is supposed to look like. This is a 3-period model, and we understand all the intricate calculations, but we want to see how it got to this point. So let's get the developer open. And it's just sitting right here, the whole thing. Now, if you notice, a lot of this code is really just documentation. It's designed to get us ready for what's coming. Okay, now, let's see. I don't think I can make this any bigger. But what I can do is copy this into a Word document. See how if that helps. Yeah, all right, that should do it. So there's a lot of new features here that we need to be comfortable with. So first things first, you might remember from the last class, of any VBA program that we might write, either it's going to be a function or it's going to be a subroutine, which is also known as a macro. Okay, and usually a function is reserved for cases where you're going to have one input and one output, and that's it. Although you can have multiple inputs, just one output. Okay. So here that's not the case, obviously. So we'll write it as a macro. And so here's the notation that we'll be using. And so you can see, I mean, they look pretty straightforward. These are the ones you saw on the spreadsheet. S0 for the initial asset price. K is the strike, T is the time to maturity in years. R is the risk-free rate of interest. Q is the dividend yield. If we don't need it, we just set it equal to 0. N is the number of time steps. And by the way, when we've written this code, you'll see that it's easy to do interesting experiments by changing some of these parameters and seeing what the results are. Or else, sometimes it's interesting to keep increasing the number of time steps and see how close your value gets to the true Black-Scholes model price. In fact, I'm going to show you an interesting diagram for a second here that is relevant to this. Imagine yourself having your code written and you say to yourself, I'd like to really know what is the relationship between the number of time steps in my model and how close my price is to Black-Scholes. Well, it's going to end up looking something like this. Here's your price. Black-Scholes is here. Okay, so anything above this line means you overpriced it. Under there, below, of course, you're underpriced it. Here's the number of time steps. So initially, with a few time steps, you can be pretty far off, although you might get lucky and not be too far off. But what's supposed to happen, something like this, meaning that initially the errors can be quite large, but if you keep increasing the number of time steps, they should shrink steadily. And if you notice that there's a tendency for us to alternate between over and under pricing, but eventually, as we get into a large enough number, um, the we're getting closer and closer to the real thing, to the actual Black-Scholes price. And eventually it will be within some tolerance of the true value. So in a way, this is no different than doing an experiment where suppose you want to know how many times you have to flip a coin before the proportion of heads is exactly a half, or at least really close to it. It would be the same idea. Okay, if you flip the coin twice, you might get two heads without a high degree of regularity. But if you flip it 2,000 times, the chances of getting way off from 1,000 heads is very, very remote. Okay, so as you get more and more time steps, you're going to get closer and closer to the true value of the Black-Scholes model. So if this is the pattern that's being developed or shown with the results, that means that your model is working well. Okay, if it's going all over the place, of course, let's say more time steps means you're getting further away from the true solution, then clearly something's not right. Okay, so as an experiment, you can try something, and you'll see that it's not difficult to do this. But anyway, so again, these are the constants we need for the problem. dt is delta t. P is the risk neutral probability moving up. One minus is one is down. Disk is, like I said, just short. I didn't know what else to call it. That's disk. Okay, we need this. We're going to discount all the cash flows in the trees. U and D. Now, indices, remember, we're eventually what we're going to do is take our trees and turn them into matrices. All right. So in other words, and this can be done in many different ways, by the way. This, you can imagine, turns into something like this. It's because it's the only way this is going to work. We have to have some way of referring to all these nodes with an index of some kind. So normally what happens is this would be the time step. And then we have to have a step which refers to how far up and down we've gone. Or you can think of as the level. And you can think of this, for example, as j equals, let's say, 1 and 2. And so this matrix is taking the place of this diagram. Now, this, as you see as we go along in the course, the whole book and the one that we're using to implement it, the Klulau and Strickland book, sometimes they do it differently than others. It depends on what model we're implementing. Sometimes they'll start with the zero. Sometimes they'll have negatives. Sometimes it's all positive. It depends. In each case is different. Okay. But the bottom line is these are not well suited for computer programs. That's why we have to turn them into a matrix, so we can easily refer to all those cells with rows and columns. Okay. So anyway, now here's a couple of other things we need to know. In VBA, an array is written like this. It must have these parentheses to be defined as an array. Once it has that notation, at some point you're going to have to tell it what are the dimensions. And that's up to you. It's your decision. You can have it as big or small as you want, but it needs to know because it's got to find storage space for it. And so even if you don't specify it immediately in the program, you can actually take care of it when you really have the information you need. Because sometimes when you write code like this, you're not sure yourself how big the matrices are going to be. So, but at some point you have to say, listen, I need it to be this size and, give me enough space to do this. So these are arrays. They can have as many dimensions as you want, but just be aware of a one-dimensional array in Excel, or VBA, I should say, is a vector, which could be a row or a column, and a two-dimensional array is a matrix. They don't call it that in VBA, but that's what it is. Okay. They do have, by the way, if you're interested, they have three-dimensional and four and five. I don't know how anybody could even visualize what they're doing with those, but they're available if you need them. So here we're going to at some point just specify not just how big they are, but what kind of data they can contain. All right. Are they restricted, for example, to integers? Can they be any real numbers? Do they have to be words? Things like that. Now, down here, dim means we're telling VBA that we expect to define these variables, although we don't have to tell it any of the details just yet. In fact, VBA is so forgiving, you could leave these out, but I don't think it's a smart move. Part of the reason for putting these here is to help yourself remember what you're defining, so you don't run into any naming conflicts. Now, having said that, you must at least tell it to expect these arrays. Okay, if you left that statement out, it would definitely not work. When it first encountered any references to S and F, it would say, "What are you talking about?" These are optional. These two are not. All right, now the basic details of the problem, the information from whatever it is you're trying to do, can be read directly from the spreadsheet, which is what happens here. And this is not the only way to do this, of course. I mean, what we're doing here is not necessarily elegant, but it works. Okay. So in other words, this is the information right here that it needs to work. This is the output. So what we're going to do is when you type these in, the commands that you need to read them in are here. For example, S0 is cells 4,2 dot value. Now, that is traditional matrix notation. It's saying look for the value of S0 in cell 4,2, which in Excel, so that means row 4, column 2. In Excel speak, I guess, Excel's own internal language, that means you look at it, row 4 is here, column 2 is here. They're talking about cell B4. Now, if you don't like this notation, there's an alternative way of doing this. Like if you're so used to these letters and numbers that you'd rather do it that way, you can replace this with and if it depends on, but I think it's good that this reinforces the matrix notation, meaning that we know this is in row 4, column 2. And this way you can actually use this information in a formula if you need to for some reason. Like if you're not sure where something is located, you might be able to write code that lets you look for it based on this matrix notation. So before, it's convenient, I suppose, but for mathematicians like us, it's not ideal. Okay. Now, by the way, I just want to show you a fun feature about Excel. Suppose that you're really a math purist and you say, listen, I can't deal with this A and B stuff. One of the settings in here will let you change it to make proper matrix notation, options, customize, no, not customize ribbon. It's, oh boy, where is that? Here it is. You see here, R1, C1 reference style. If you click that on, dare we try it? Look what happened. Oh my God, where's the A's and the B's and all the rest? It's gone. Okay. So let's undo that and put it back to where it belongs. Okay, just in case you would prefer it that way, if it makes it easier for you to write code. Anyway, so the others are the same. It's just telling it where to find it. And you notice you must have this dot value to let it know that what you're looking for is the value as opposed to the formatting or something like that. Okay. So that's going to read it in. So internally to VBA, it has a variable called S0. You can ask it to print it out and make sure that it has what you think it has in it. Okay. As a double check. Now here, this is actually just straight ahead computation. These are the constants of the problem. And here we really are double checking these by printing them out to make sure they look right. Okay. In other words, if you can say, listen, I've calculated DT correctly, but how do you know? This is a good double check. You have it printed out here, and you can look at it and say, something doesn't look right. And this is one of the ways you can find out if possibly there's an issue here. So it will calculate these. And now here's where we have to get used to some of the commands in VBA. I think I mentioned before that VBA has some of the same commands as Excel. And keep in mind, VBA is a very old language. Okay. I think we're talking about like the 70s, if not older than that. So there's a lot of clunkiness that we have to contend with. And this is among those clunky things we have to worry about. There's functions in both, like for example, square root, perfect example. The Excel version is spelled actually there's no uppercase there. There usually isn't any case involved with these commands. Sometimes one way looks prettier, and what you'll notice when you type in VBA, it tends to adjust things the way it likes them, but there's no case sensitivity here. So SQRT is in Excel and VBA is SQR. So the rule here is that always use the VBA version if it's available. Now, here's the wacky part, though. If not, you must add dot application. And that's literally what it said, a dot and then the word application to the end of the VBA function. I'm sorry, that's the Excel function, so that it knows that this is an Excel command. Otherwise, it doesn't know. It's like, what are you talking about? Like what would be a good example of this? Something that is only in Excel. Um, uh, like I think let's say variance. Actually, I'll tell you, let's use correlate. In other words, if you need the correlation for some reason, it's not going to be in VBA, it'll be in Excel, but in order to invoke that command, you have to say correl dot application because this is the Excel, this is the name of the Excel function. The dot application tells it where to find it. Okay, if you leave that out, which would be easy to do, it won't find it. Here, though, the SQR is the VBA version, and so it's fine, it's happy with that. Now, do not use application with the VBA's own function. It won't like that either. Okay. So anyway, so here we got some more calculations. Oh, here's another one, EXP. Now this one is in both, if I'm remembering correctly, but it's spelled the same. So you can just use EXP. EXP means e to the x. Okay. So you'll often see, like here, you notice how U is defined as e to the vol is this standard deviation remember. That's what this command is saying. And then the p's, you might remember the risk neutral probability is this. And then 1 minus p is just 1 minus that. Okay. And then disk is e to the minus r delta t. All right, and we'll use that to discount all the cash flows. Remember, the whole point of all this is that we're using a risk neutral framework. And so all the cash flows will be discounted by R, the risk-free rate of interest. And everything, again, is done in risk continuously compounded returns. Redim. Now, here's where you actually specify for the first time the size of your arrays. Now, if you notice the way it's written, the redim statement is basically saying, remember that S that I defined earlier as an array? Now I'm ready to tell you its dimensions. Same thing with the F. So here it's written as 0 to n, which means S will look like this. Oops. What did I do? Now, I don't know if this is actually correct, but I like to visualize these more like this. I think that when we start writing code and start going through these examples, I think you'll find that it's easiest to visualize it a vector in VBA like I have here as a column vector. I mean, the row vectors are very awkward to deal with, I think. And then of course F is the same thing. So in other words, now where do we put them depends on what the numbers refer to. The numbers could refer to, well, the actually you're going to have one column for each time step. The way we're going to manage this is that um, we'll reserve one column for each time step typically, and then the height, in other words, the difference between these two would refer to how many branches we've gone up or down since the start. Right. So we have to think of this whole column vector is a single time step. And then within the time step, these are all the possible movements that we've had, up or down. So we'll see when we get to a specific example. Now, once these constants have been calculated, here's how we print them out. Now, if you notice, let's look at these carefully. Cells dot value, we read them in. Oh, actually, no. Cells dot value here, if you notice, K is assigned whatever is in cells 5, 2 dot value. So this command means read some information off your spreadsheet and assign it to variable K. Whereas here, it's the other way around. This is saying whatever's in DT, whatever in DT you just calculated, print it out in cell 13, 2, which is B13. Same thing with all the others. So that's where this comes from. Okay, it reads these in, and the way the code is written, its first job, let's say, is to figure out these constants before it goes any further, because it'll need them. All right, it's like, I guess, a carpenter showing up for work. He opens up his toolbox, takes out the hammer and the saws and the chisels and the wrenches and all the rest. So he knows where they are, then he can start building. Okay. Now, this is where it gets exciting. And this is where it gets very complicated. Oh, there's one I couldn't think of it, max. Max only exists in Excel. So if you want to use max, it has to say application dot. And you notice the actual code is very short. Everything up to this point was basically housekeeping. We were explaining what we're doing with the documentation. Then we were reading in the input into the program. We're calculating our constants. It's like getting ready to cook. You're getting all your equipment out and the ingredients and getting them right in front of you. Now we can get started. Okay, the actual cooking, so to speak, is here. And it's surprisingly straightforward because it's set up very efficiently, shall we say. And it requires a bunch of loops, as you'll see. And that's a bit of a complex structure, but what it does is it enables you to go through a process as many times as you need. And without having to write like hundreds of lines of code, you can just say, do this, change the index, do this, change the index, do this, do this, until the index reaches a specified value. So that's what all these are all about. But the first step is to initialize everything, set up the trees, and then we're going to grind out the results. So it's deceptively simple looking. So right about here is where the hardcore programming begins. So I think that's where we can start next time. All right, I think we're in pretty good shape now. So we understand how this binomial option pricing model works. And we're going to do actually several of these examples. We're going to do European calls and puts, and then we're going to move on to American calls and puts, where we're going to see how this code has been updated to allow for the early exercise. And then we're going to see how we could do the same thing for exotic options. And then we're going to see how we could use this setup for calculating the Greeks. Okay, so yes, this is going to get very complicated, but once we understand what the logic is, you'll see that it's not that bad. All right. Well, anyway, I guess we've had enough fun for one night, so we'll just knock it off here. And then next time we meet, this is where we'll pick it up. Okay. So I'll see you then.